All right, welcome everyone. So we're going to be trying to learn about shaders in this tutorial series. And as you can see, hopefully by the end, our goal will be to just do some very simple ones like, making this guy glow, and we're doing that glow through this kind of shader over here, and then make this, heinous looking fire. And obviously there are much better tutorials on how to make much nicer looking fires. But what I was finding with the tutorials, whether it was GDQuest, who has an excellent tutorial series, or just looking at how these at how to make these things, I was really getting lost. And so if you're one of these people who, like me, really struggle with shaders and what they mean and what all this code is when you see it, I'm going to try and demystify it a little, at least how I understand it. A few caveats: I am by no means an expert at shading. I think these shaders require a whole lot of and we're just going to be talking about 2D shaders. When you start getting into the 3D shaders and you have to start looking, it really adds a whole nother dimension and really gets an order of magnitude harder to go through. But I think at least if we can do some simple ones, we'll start to understand what all these words mean and all these things like UV and uniforms mean, and try and just solve some simple problems. And hopefully by doing that over and over and really hearing and seeing the same thing over and over, we'll start to hopefully you'll start to understand, because like I said, programming and game development is definitely not my day job, and I am very far removed from some of the math that from college. I am a late Gen Xer, so college was quite some time ago, and even though I took calculus, my memory of it is pretty poor. But we will be going over some of the math that you need, like especially using sine waves and cosine, or mostly just sine in this example, to sort of develop these repeating patterns, and then learn how to texture it. So one of the resources I found immensely helpful, and I definitely think you should go take a look at it, because this is what finally things started to click, was when I read this book, and it's called thebookofshaders.com. And it is free, although, obviously he suggested donate to him, and I would fully support that. The only thing is I can't really show you or walk through step by step, because I do not have copyright, and this is not a Creative Commons licensed asset, so we'll just kind of move it off to the side, but we'll still kind of go through it, because I think the approach is really great. And like I said, I would very much encourage you to read through, especially the first chapters. My one criticism of this is once you start getting into, it's supposed to be a gentle step-by-step, but I would say there's a few places where things get a little bit complicated a little too soon, I think. But hopefully we'll try and remove a little bit of that complexity, at least when we get started. All right, so without further ado, we will not be ending here on this first tutorial video, but hopefully by the end of this little series, we'll get to here. So without further ado, let's come here and let's just make a brand new blank project. All right, and we'll just make a new project, and we'll just call it Shader Fiasco. Create the folder. All right. And sorry, let me resize it. All right, let me resize this too. It makes you feel like you're on Mac OS when you're doing this. All right. So hopefully this will show up in OBS okay. All right, so we're going to start with just a boring old 2D scene. We'll just, call it world for fun. And the first thing we're going to do is create just a boring old color rect. And here we are. We have our color rectangle. And the other thing I'm going to do is, just so this shows up a little bit bigger on the screen, is we'll just come here to our window and make this like let's make it 300 pixels by 200 pixels, and then we'll just stretch it out to do 1200 by 900. Hopefully my math is, no, that's not right. 1200 by 800. Yeah, there we go. All right, and now let's just make sure our window looks okay. Select current and world. All right, so here we have our just boring old white rectangle. So now the question is, now obviously we can come here, and the easy answer to just changing the color is to just use the modulate property, and you can make it purple. But let's see if we can do this through shaders. And to do that, we're going to come back to our color rect, and pretty much every canvas item has on the inspector this material tab. It has a texture, but it also has the material tab. So we'll come down here to the material, and we'll say new shader material. And now we've got this new shader material in here. And if we click it, this will pop open, and you'll see in the material there's room for a shader. And we are going to make a new shader. And we'll call it just color square shader. Okay, and so this is just all we're going to be doing is making a color, changing the color to start with. And I know that's boring, but you got to start somewhere. So so here we have the type that we can select. If you prefer to use visual shaders, you can. We're going to be doing code because in the end of it, whether you're doing visual or regular, you do have to understand the math, because you got to pick the type of nodes you want. So we'll just stick with the code to start with. But feel free to, if you prefer to use the visual shading system, that's certainly up to you. The other thing is, as you can see, there's several different kinds of shader types. The one that we're going to do for 2D, and like I said, we're sticking to 2D, is basically just canvas item. All these other stuff have to do with a lot of other more complicated shader things, and we're going to leave the default template on, just so I don't have to type in everything. I'm not going to put in a built-in shader. What that would mean is that the resource is sort of built into the node, but we're going to leave it as a separate file in the file system. And we'll just use a boring old terrible path structure. All right, so great, we've got this shader. And now we can click on it, and this will pop open this shader editor down below. And as you can see, you've got your usual stuff down here. You can always turn it off if you want more space. But you should see this shader editor, and it'll show you the shaders that you've got here. And the first line of code tells you the kind of shader type. And like I said, with 2D, it's pretty much all canvas items, and it starts out with this keyword shader underscore type, and then the name canvas item. Now, there's several built-in functions that we're going to have to know, and the first is fragment. There's another one called vertex, and the vertex is sort of for manipulating the edges and the vertices of this, so you can kind of squish and stretch and do that sort of stuff. I'm going to leave that to other people to show you, but we're going to be focused on the fragment shader. And what the fragment shader does is it basically just colors all the pixels, and it uses this C style of programming language called GLSL for OpenGL Graphics Library Shading Language, or GLSL. And the book of shaders goes through GLSL specifically. I'm going to show you kind of how to translate that into Godot. But the first step in doing that is realizing in C style programming, everything needs to end, every statement needs to end in a semicolon. You're probably used to GDScript. You don't have to put semicolons anywhere, but in this we do. There's a few other things that you kind of have to be aware of, and it's a very, I guess, what's the word, persnickety language. If you don't, let's take a float. So we'll declare a float, and we'll call it, var1, and then we'll make another, and we'll initialize it to 1. And you can already see it's going to probably complain right off the bat. And it'll say invalid assignment of int to float. Now in GDScript you can have at it, you can mix floats and ints, and it'll just automatically convert, but this language will not. So you're going to have to get pretty used to putting .zeros after everything, after all your variables, or it will complain immediately that you're not using the right variables with that. Similarly, if we declare, an int var, I guess var 0, we'll set it equal to 1. If we try and do var 1 times var 0, and just save that. See, again, complaining. So 0.0. It's again going to have a problem with you multiplying a float by an int. You must only use floats with floats and ints with ints unless you want to cast them specifically. I believe you can cast lick and see if you're familiar with it to float. Let's just see if that works. If not, yeah, no. Doesn't work. Okay. Float. Oh yeah. Okay. So you can convert a float to a float, and now it'll work. All right. So now that we know we have to deal with that kind of attention to detail, let's get started. Now, the first sort of magic variable to be aware of is color. And what color is it's a vector 4. So everything we do in shaders is going to be based on vectors. And vectors, you're probably used to. You're probably used to a vector meaning. You're probably used to a vector meaning like an arrow, that points, and you have a origin or whatever, or 1, 0, whatever it is, and then a final destination. But remember, vectors just store 4 numbers, and in this case, what color is going to store is a vector 4, but it's just going to be red, green, blue, and the alpha value. And the alpha value is the same as transparency. So, and these values will only be accepted from 0.0, so we're already going to remember to do that, to 1.0. And with 1.0 being all the red, and 0 being none, and then various values in between. So just if you think about it, if you have a vector 4, I should put the vector 4. If you have, something that's all red, 0 green, 0 blue, well, that'll just be red. And similarly, if you have red as being 0.0, green as being, 1.0, and blue being 0.0, that'll be all green. And of course, if blue is 1.0 and these guys are just 0.0, this will be all blue. And then as you add different values together, you'll end up with different colors. All right, so without further ado, let's just see how this works. So we're going to do color equals vector 4. And as you can see, it has multiple different constructors to make a vector 4. And we'll see about how to sort of change that later. But let me just pull this up so you can see a little bit more of that. But as you can see, you can take just one float. It'll take 4 floats. It'll take a float and then 2 vectors. Or a vector 2 and then another float. It'll take a vector 2 and then 2 floats. And we'll see sort of how this works. Again, you can do like a float and then vector. So it's got kind of most of the permutations that you can do in order to construct this vector. But let's just start out with doing the float for the RG and B. So let's start with 1.0 for red, 0.0 for green, RGB green, and 0.0 for blue. And remember, alpha is transparency, so if we do 0, it'll disappear because, and remember you have to end it with a semicolon, but as soon as you save it, you'll see it updating up here in the inspector, and you'll actually also see what happens to the material there. But remember, we don't want this to be transparent just yet. We'll start to work with transparency later. So we just want it opaque. So now it's red, green, blue, 0 green, 0 blue, and then we're making it opaque. And as you can see, boom, the texture or the color rectangle is now all red. And now let us just play around with some colors. And as you can see, 2 is not going to matter because there's no high dynamic range or anything like that. We're just working with the usual, so making it more red does nothing. But let's make this green. And so we've got our R, G, and B, and there we have it. We have a green rectangle. And, just hit the play, and beautiful green rectangle. And now that we lost our thing, let's remember how we get back to it. So we can click on the shader editor, or you can, click here. You got a color rect, and if we just collapse everything again, just remember you can come down here to material, and you already see that there's one change, and you can finally find your shader there. So if I come over to the debugger or whatever, and then I come here and click on, no, I guess it's not gonna, so we'll just have to come back to shader editor. All right. So great, so we kind of have an idea of what's going on with my pen, with color. And the thing to realize about what color means is color doesn't just mean the color of the whole square. What it really means is the color of each and every individual pixel. And so now we have to kind of get into a little bit of the theory of what this means, because when we start talking about UVs, it's super important that we kind of understand how this shader really works. So we now have written our first shader program, and I'm going to come to this, let's see, my whiteboard here. Oh, that is glaringly bright. Let's see, is there a dark mode? No, maybe format background. All right, sorry if I blew out anybody's visions with that. So the idea of the shader is that we have our computer screen. I'm going to draw a really terrible rectangle here with this drawing pad. And this is divided into individual pixels. And each individual pixel will have a red, a green, a blue, and an alpha value for the opacity. And basically each and every one of these pixels has that, and that's why you see the different colors on your screen. Now the thing is, if you wanted to draw an image, you could do one of two things. You could use the CPU, and you could just tell each and every pixel one by one in a nested for loop, right? You could go for, you could do from, for x in range, 0 to, let's just say this is a 1920 by 2080 monitor. You could do to 1920, and that'll scan through all of these pixels, and then you could do for y in 0 to, and then let's say it's 1080 to 1080, and then you could draw each and every single pixel based on where it is. But obviously that's not going to be very performant, because as you probably have learned by now, going one by one in a for loop is very, very slow. Now you can do powerful things with it, but it is going to be very slow. So what a shader does, and if you look, let's see if I can pull this up. So I've got a NVIDIA 2070, and I have an AMD Ryzen 5600X. So if we look at the specs of the Ryzen 5600X, why are you not dragging? Oh, it's because it's trying to drag out there. So here, I'll just bring it over here. So if we have this Ryzen 5700X and we ask how many cores, it's got 6 and 12 threads, which means you can at best divide this whole screen up into 12 individual segments, and maybe like 3 by 4, and send this one to one thread, and then this part of the for loop to another thread, and that'll get you a little bit more performance. But if we come here and look at our at my NVIDIA 2070, and I look at the specs, you'll see that it has 2,304 cores. So as you can imagine, that is going to be a lot more threads that it can handle. And if we look down here, you can see the pixel rate. It can go through 103.7 billion pixels per second, shading them and running code on each and every single pixel. So as you can imagine, instead of having to divide this screen up into just 12 segments, I can divide it into 2,000 segments, and each core will only be responsible for running a few of these programs. Now, the tricky part about that is, though, the GPU, while being very, very fast, it doesn't have any memory associated with the last thing it did. So basically, if we want to figure out how to address each pixel, and obviously we do need to if we don't want to just stare at solid colors all day, no, I don't want a new Godot. Let's see, where are you? So if we don't want to just stare at a boring old rectangle all day, we need some way of changing this code, because remember, this code is going to be run to basically every single pixel will run this code. We need some way of distinguishing this pixel from this pixel from this pixel, if we zoom up, from this pixel from that pixel, and somehow that way we can create shapes, we can texture our objects, we can do all sorts of things, but we need to have some sort of way of addressing each one individually such that we can use the math in here to change our behavior based on where we are located in the texture. And I hope that makes sense, but the way we're going to address the space is with another variable, and those are called UVs. So let me just see, let's erase here. All right. So what UVs stand for, and it'll be a little bit confusing in Godot, honestly, because what the UV stand for, this doesn't stand for ultraviolet or anything. It's really just the axes. This axis, the width, is U, so it's basically like X. And V is vertical, I guess, and that would traditionally be the Y coordinate. And and just from Godot coordinates, we remember that up here is the 0, 0 pixel. Over here will be let's just assume, again, this is the 1920 by 1080. This will be 1920 in the X direction and 0 in the Y, because we're still at the top. This one down our X-axis, which is 0, will be 0, but we're moved all the way down, so we're now at 1080 in the Y direction. And over here, in this part of the screen, we've got our full 1920 by 1080. Oh, let's see, 1080. Okay. So that's great. Why do we use a different naming system rather than just X and Y, since we're used to X and Y? The reason for that is because, one, when you're dealing in 3D coordinates, you actually need a third one called W. And then the other issue is we already have an X and a Y. We know our position on the screen is X and Y, but we want our textures to be a little bit different. And if you're trying to map those, especially into a 3D realm, you're really going to get confused between which X do you mean. So hence why we use U and V. Now, unfortunately, in Godot, when you try and access the U and the V component, it's not uv.u, it's instead uv.x. So just be aware of that. What that really means is now in the UV space, we're talking about the X coordinate. So, but why do we need this other system? The reason is, you can imagine where things would get complicated is, let's say somebody else has a 2456 by 1440p monitor. You can already see, oh my goodness, we're going to have to write a shader that not only handles the 1920, but if somebody else wrote some really great code, we are stuck with now having to change it all to this other monitor's resolution, and we're going to have to figure out the monitor's resolution, blah, blah, blah. So this is where things get a little bit more complicated. So in order to address this issue of multiple resolutions, or let's say you have a square that's 200 by 200 and then you want a different square to be 400 by 400, in order for our shader to work, we need to normalize these. And the easiest way to normalize something is just take a percentage of it, right? So rather than saying, oh, I want, this fourth pixel here, right here, and that'll be, 4 by 0, I can use a percentage of the screen. So I know like this is, let's say, I did not mean to zoom in. Let's see, can I zoom out? No. Okay. So let's say I want to address this third pixel right here. Come on. And it's about a third of the way through down, and maybe it's, you know, another third there. I want some way of just saying, I want, regardless of how big this is, I want a pixel that is in the first third x direction, the first third y. So basically, in order to establish this UV system, you basically just take your pixel coordinate. Like, let's say I want, you know, let's see, what would be, let's just break out our little handy dandy Windows calculator. Where are you? There. Oh, and this will save for a little bit later, so we'll just make a new calculator. And let's say I want pixel, you know, 1920 times 0.3. You know, so let's say I wanted pixel 576 by, you can already see what I'm doing here, right? By 360. I can take 570 and divide it by 1920. And now I know that in my x direction, I want something that's 0.29. I want the pixel that's 0.2968% of the way across the screen. And I also want the pixel that's in the y direction that, what did we say, was like, oh, let's see, was 360, you know, 360 divided by 1080. And I want that in at 0.33. So now my UV coordinates for pixel, let's kind of move this off to the side a little bit. So now my UV coordinate for this pixel isn't, you know, 570, comma, my goodness, my brain, 360. It's actually coordinate 0.296875, comma 3333. So that'll get this exact pixel that's not quite, you know, 1/3 there and is exactly 1/3 here. So I hope that kind of makes sense, that the UV per pixel is calculated based on a percentage. So rather than our UV coordinates going from 0 to 180, it'll go from 0 to 0.0, so I caught myself again, to 1.0. And basically just 0.0 being the percentage. So 0.1 would be the pixel that's exactly at 1/10. You know, 0.5 being the pixel that's exactly at halfway through whatever, you know, texture we're working with, and over here will be, of course, 1.0. And the same goes for, this is the x direction I'm talking about, and then of course the y direction is the same, from 0 all the way up here to 1.0 down here. All right, so I hope that's kind of starting to make sense, that the UV coordinates, that when we're trying to address a pixel, we need to use these UVs, and these UVs are going to be normalized to between 0.0 and 1.0. All right, so that's that. All right, so we've kind of learned about UVs now, and how do we address the UVs? Well, it turns out that there's another hot keyword called UV, and the UV is basically a vector 2, because it stores an x and a y value, or rather the u and the v value. So we can say, you know, we can say vector 2 equal vector 2 my vector equals the UVs. And now we're going to watch what happens when I put this vector. So remember, we can just stuff a vector into your 2. So for instance, just to make this a little bit more clear, before I go breaking your mind for the very first time, right now we have this vector 4, but we can actually remember from this constructor, we can construct it with a bunch of different ways, and we can do that by making a vector 2, just like this, and we can put in another vector 2 right here to handle the green and the alpha. And we have to make sure our parentheses all match. And now when we do it, it's the same, because if you think about it, red is just the first portion of the vector, green is the second portion of the vector, blue is the 0.0, and 1.0 is the alpha. So just so you are aware, you can split this up, this vector 4 up into smaller values. What happens, so we know that the UV is a vector 2, at least in the canvas item, because we're not dealing with, we're not dealing with three-dimensional space, so it's a 2D vector. So if I do put in a UV2, we're going to have an R and a G component, but look at what happens when we make the, so it's the RG, we'll make the blue 0, and we'll make the alpha 1.0, so that way it's opaque and we can see what's going on. And all of a sudden, instead of having a solid color, we have this really neat gradient being formed. And why is this gradient being formed? What's going on? I mean, I didn't specify to put in a red here or a green down here. So what is going on here? And this is where this sort of magic variable comes into play, this UV. This UV is not a single one-point variable, if you are catching what I'm saying. But what it is, it's really, if you think about it, a matrix of all of the possible values from 0 to 0.001, comma 0. Oh, I'm sorry, so this is y, so I've already messed up. So let's see. So what this really is, let's just draw this here. What the UV is it's not a single variable. The UV is going to depend on where it is in space. So here we'll just make like a big kind of matrix, and it'll have a bunch of different values, basically a lot of different floating point values that will represent every little spot. So here we have, in the very top left, we have our 0, 0 pixel, 0.0, comma 0.0 pixel. But halfway down, we have a value of, so this is the y direction, so we're still at 0.0x, but we're now at 0.5y, or rather, if you prefer, v. And then here we have our pixel down here, which is still 0.0 in the x direction, but it is 1.0 in the y direction. And now, if we think about this pixel right here, this guy is, would be, now we're moving in x, so it's 0.5 in the x direction, and we're at 0y still, 0.0. And over here, this is the very end, so we've got 1.0x and 0.0y. And down here you can think about this one, we'll just for the sake of completeness, this one is now 1.0 in the x direction and 0.5 because we're halfway down the y direction. And then finally we get to our bottom pixel, which is going to be 1.0 and 1.0. So rather than thinking of this UV as just one value, what it really is remember, this function is basically being sent to every single pixel on the screen. This one right here, to this one right here. And obviously there's a little bit more to it, since there's obviously not a core for absolutely every single pixel, but just for the sake of deciding, just for the sake of explanation, we'll just assume that every single pixel has its own exact thread. What we're saying is the UV of this pixel, so when we send this code to the GPU, this UV is no longer just UV. This gets the value of this pixel right here, and let's just assume that this is what? This may be like 80% in the x direction and maybe 90% in the y direction. This code is actually going to be sent to this pixel here, with the value 0.8 comma 0.9. So no longer is it a UV, it's just a straight old one vector value, and then that value gets stuffed in right here into our color. And what the color is the color is this color only is for this pixel right here. And so we know that the color of this pixel, we're going to base it on the vector 2 of this value that's changing for every single pixel. This value is going to change. And so now all of a sudden you can start to see what's happening here. So the color of that exact pixel, and actually let's pick an easier pixel to do. Let's pick this pixel up in the corner, which is red. And we know that that value is that the UV value that's being sent to this is going to be 1.0 in the x direction and 0.0 in the y direction. Well, if you think about it, we've just created a vector 2, and we just stuffed a vector 2 with 1.0 and 0.0, followed by a blue value that's 0.0 and an opacity of 1. So what is that going to be? Well, it should be red. Right? Red, green, blue, zeros, and there you have the red color. Now, if we come down to this pixel down here, we have the exact opposite, right? This pixel down here, we know the U and the V values that's going to be sent to the color of that pixel, the color of this pixel right here. Ooh, and I'm starting to get messy, so let's clean this up again. So, so here we have this pixel right here, and this pixel value, or we can say that the pixel 0.0 in the x direction and 1.0 in the y direction is going to equal a color that is now, well, we know which pixel that is. That's 0.0, 1.0, and 0.0, and 1.0. Right? So this 1.0 gets put there, this 0.0 gets put there, and then this UV for this exact pixel is going to be 0.0, 1.0, and what do we know that is? Well, that's red, and that's green, and that's blue. We have 0 red, we have 0 blue, but we have all green. That is a green pixel. So now, hopefully you're starting to see that as we change these, as we go into different pixels, the color value of that pixel will get determined based on its location. And in this case, we've done, this would be, just to go back through one more time, 1.0, 1.0, right? This is the very bottom right pixel. And so the color of the very bottom right pixel is going to be given this value of 1.0, 1.0, 0.0, and 1.0. And as we know, red and green, at least in the light colors, makes yellow. And that's why we see a yellow pixel. So let's just go changing where we put the UV vector and see that, that things will change a little bit. So we know that we've got red and green, but let's stuff this into the green and blue space. So let's start with a red value of 0.0. Now let's put the UV vector, and let me just get rid of this since we don't need it. Now we've got this UV sitting in the green and blue space, and its opacity is 1.0 in all the pixels. So all the pixels are going to have this opacity of 1.0, and all the pixels are going to get a value of 0.0 for the red. But just like we did before, we now have this vector 2 that's got all the different locations of the screen on it. So we've got down here, this pixel, remember, was x was 0.0, y was 1.0, and we've got so we've got this vector being 0.0, 1.0, and so we've got a red value of 0. We've got a blue value, or sorry, green value of 0, but we've got a blue value of 1. And what does that make? It makes blue. And as you can see, when you mix, when you have all 1.1 of green and blue, you get cyan. And then over here, of course, if you have 0, 0 for everything, you get a black pixel. And over here, we've got 1.0 in the x direction and 0.0 in the y direction. So remember, we got, oh goodness, so we've got 1.0, oh, sorry, the red stays 0.0, right? But we've got in this vector 1.0, 0.0, and then an opacity of 1 for all the pixels. And as you can see, we've got red, green, blue, and this is green. And green is 1. What happens, let's just, for the sake of fun, move it one more to the right. And I can imagine this is just super fun. But let's put the UV here. And now we're going to have a different thing, because now all of a sudden our transparency is changing, right? We've got red, green both being 0. Blue will now be positive whenever the U portion of the UV is 1. We'll have a nice dark blue. So we'll go from, here's the U value. Here's the U axis, also known as X. But we've got the U axis going this way. So if we come here, we'll go from black color to solid blue. But what's happening in the Y direction? Well, the second part of the vector is now the opacity. So the UV dot Y parameter, or rather, the V part, is going from 0.0 to 1.0. And so we start out at essentially completely transparent, right? The alpha is going to be transparent up here, but the alpha as it comes down is going to be 1.0. And so you can see this really neat. So if we just kind of pointer you off to this side over here, you can see it's very transparent when the Y value is 0, but it gets more opaque, and of course it's going from black to blue. So we've got this nice translucent color. You can obviously break down the UV into its component parts, and you do that with UV dot. And if you look, there's, unfortunately, like I said, there's no U and V. There's no UV.U and UV.V, which would probably make the most sense. There's just UVX and UVY. But let's just look at changing the transparency based on just the X value. So rather than giving it a whole coordinate, we'll give it just a part of the coordinate. And this is a problem here. So now the UV.X is actually a float value. What is the problem? Oh, right, because we don't have all of it. So we're just going to look at blue for now, and we'll make these all opaque. So now, if you look at it, the UV.X is just the X component. And as you can see, if we're just looking at the X component, the blue will go from 0 in the X to 1.0 as we move down the line. And now all of a sudden we're losing that whole sort of weird gradient effect. Why? Because we're just looking at UVX. So let's just kind of go through that for a second and see if we understand why that's happening. So again, we made a vector for, this is the red, this is the green, this is the blue, and this is the alpha. And so for all the pixels, we know the red is going to be 0. For all the pixels, regardless of where you are, it's going to be, the green is going to be 0. And for all the pixels, it's going to be fully opaque. But for the blue pixel, we're now basing it off of this UV.X. And this UV.X, remember, is a big matrix. It's not just one value. It's going to vary depending on where you are in the material. So let's say let's just take a pixel here. Let's start in the top corner where my value is 0.0. And remember, this is the UV, and this is 0.0. Well, I'm only going to take the X part of that. So if my UV.X is blue, then the pixel here, which is going to be, let's say, pixel, or actually let's, so I'm only going to take the X component. So if we look here at this pixel here, this UV's X is 0, right? And this pixel's UVX is 0. And this pixel's UV.X is 0. They're all 0 right at the border. But as we come here, all of the UVX's are going to be 1.0, because remember, we've stretched all the way across. So now all our UVX's, no matter where you're at. So if you just pick any old pixel, it's going to totally depend, your blue color is going to totally depend on where you are only in the X direction. It has nothing to do with the Y direction. because even though the y component of this one, let's just say this is a third, so we'll do 0.33, and let's say we're a third down, so 0.66. So the color of the pixel at 0.33, 0.66 is going to be red of 0, green of 0, but blue is going to be 0.33. So it's going to be pretty blue, but not, not 1.0 blue, not the brightest blue. Even though we're down. And so it doesn't matter where you're at in the y direction. It only matters where you are in the x direction in terms of that. So as you can see, we can slowly start to manipulate these pixels going this direction. So I hope this was helpful. This will be just the very start of where we're going with this, but as you can see, we can kind of play around a little bit with these values. So let's just make this 0.0, and it really helps to kind of do it yourself and play around. So obviously now every pixel is black because it doesn't matter where it is. But let's say I do my uv.x here. Now, of course, it's going to be very red, and obviously red is a very bright color. So as you start to get brighter and brighter towards the x direction, you're really going to start to see the red coming out probably sooner. If you can see, and I'm not sure how the compression will work, you can still see, at least on my monitor, that it's still kind of this darker red, but it's really going to come out brighter. And then of course we can do uv.x here, and if we move it, now we have green, right? And green is also a bright color, so you'll see over here in the x direction, all the pixels that are on this stage will be black, and then all the pixels as we get closer will have bigger and bigger green values as we get more and more to the right, and the UV value of each and every of those pixels, X's value gets bigger. And of course you can play around with the Y one, no reason not to. So let's do Y, and now all of a sudden you see the gradient shifting to the top. And why is that? Well, if you think about it, all of the Y values up here are 0, right? So if we have our UV vector, and we have our x, the x is going to change across here. It's going to go from 0.0 to 1.0. But all the y's at the top row are all stuck at 0.0. So if you're a pixel here, your y value is 0.0. If you're a pixel here, your y value is 0.0. And if we're going to set the green channel to be the y component, then everything at the top row is going to be 0. Everything at the middle row is going to be 0.5. Everything at the bottom row is going to be just full-on 1.0 bright green. So now we're losing that sort of trippy gradient we had before because we're just picking the value based entirely on that. All right, so I think we'll stop here for the first part of UVs, and then we'll start to play around, I think, in the next one with these variables called uniform, and we'll see what those do and how we can actually use GDScript to influence those variables. And we'll almost basically repeat this, but then kind of linking up GDScript with this so we can play around with the colors without having to change it every time in code. All right, good luck. And like I said, definitely look through that book of shaders. Like I said, it does get a little bit more complicated as you go on, but it is certainly, if the first few chapters are worth a read to begin with, and I think it's a really good resource. And hopefully now you at least kind of have learned the Godot keywords to get it going. Color, so just to give you a little bit of a cheat, and again I'll have to move this off screen so I don't end up with a DMCA takedown. If we look at the Hello World chapter, he uses this thing called GL frag color, and that frag color is the same as this color. It's the representation of every single pixel per thread, per little pixel of the thing. And then of course when you're starting to look into UVs, he'll use another one. They'll actually calculate that. They'll actually calculate the the values of the UVs. But in his case, their case, because I believe it's Genlo and just so I don't butcher their names. Let's just go back for a second. Patricio Gonzalez Vivo and Genlo, and they together, I think, made this really excellent book. And they'll use GL frag coordinates, and that's their way of calculating the UVs. But fortunately, Godot has made our life a lot simpler. Rather than having to do GL frag color, we just say all caps color, and rather than having to calculate the frag coordinates and normalize them to the UVs, which he'll show you how to do in the book, or they'll show you how to do in the book, you will start to see this. You will just see UV here. So we already get UV, and then you can access the different components with UVX or UV.y. All right, so I think that was a long enough intro and a long-winded sort of guide to just getting started with them. But like I said, hopefully we'll do a few more in the next little bit and get to those things I showed you in the first part. All right, let's turn this off.